This video clip, we're going to take a look at some pre-lab information for our acid-base salt pH lab, specifically focusing on the part 3 of our lab exercise. To start, let's take a step back and focus again on the Bronsted-Lowry definition of an acid and also of a base. According to the Bronsted-Lowry definition, an acid is something that is a proton or H plus ion donor, whereas a base is something that is a proton or H plus ion acceptor. For example, hydrochloric acid, as we look at this reaction, the hydrochloric acid is going to donate a proton to the water. In this case, the HCl donates the H plus to the water molecule. The water accepts the H plus and turns into an H3O plus or hydronium ion. In this case, the water is acting as a base by accepting the proton. As this takes place, what happens is the concentration of the hydronium ion concentration is going to increase, and this will now make our solution acidic. Now, for this particular chemical, hydrochloric acid, by this point here, it's fairly obvious it's an acid. It starts with a hydrogen. It can lose that hydrogen by donating it, functioning as an acid. That causes the hydronium concentration to increase, and our solution becomes acidic. However, surprisingly, there's some things that lack a hydrogen, yet they can still function as acids. The things that can do this are metal ions other than those that come from columns 1 and 2 on the periodic table. Essentially boils down to it's mostly the transition metal ions that can function as acids. Now here's what is believed to occur and how a metal ion can make a solution acidic. We have a metal ion that's not from columns 1 or 2 on the periodic table. We have our iron 3 plus or our ferric ion. The water molecules, a certain number of water molecules will move in towards the iron ion and essentially stick to the iron ion. This iron ion, now surrounded by water molecules, will behave as if it's just one particle. Now, what we have here, it's known as a sphere of hydration that now surrounds our iron ion. And this will behave as a single particle. What can happen now is that one of the water molecules that's attached to the iron can lose a proton to the surrounding aqueous solution, and in this way the iron surrounded by the sphere of hydration of water molecules can behave as an acid. What happens is one of the water molecules in the sphere of hydration surrounding the iron ion donates a hydrogen, H plus, to the water. The water turns into hydronium ions. The amount of hydronium ions increases, and the solution becomes acidic. In this way, the iron ion, even though itself individually lacks H plus ions, by forming this sphere of hydration with water, it can function as an acid by being able to donate an H plus to the surrounding solution. Therefore, a salt, such as iron 3 nitrate, will end up making the resulting solution acidic. Looking at our salt, the ions that form the negative ion nitrate, that's the conjugate base of the strong acid HNO3. Because it's the conjugate base of a strong acid, the NO3 minus ions will end up being a spectator and do absolutely nothing to alter the pH of the solution. The iron ions, on the other hand, because they're metal ions that do not come from columns 1 or 2 on the periodic table, the iron ions have the ability to make that sphere of hydration, which can then donate an H plus to our aqueous solution, and this particular salt will end up making a solution that is acidic. Okay, let's turn our attention to some other stuff about salts and pHs of solutions. Now, to introduce this topic, let's first take a look at something like an amphibian which we know is something that can live on either land or water, such as a frog. And then we have the term ambidextrous, which indicates someone can use either their right or left hand or feet equally if someone's ambidextrous. And our last thing with this prefix little am part was something known as amphiprotic. Something that's amphiprotic can behave either as an acid and donate H plus ions, or behave as a base and accept H plus ions. So our next topic is going to look at these specific ions that have the ability to be amphiprotic, where they behave as an acid or as a base. An example of something that can demonstrate amphiprotic behavior is the ion bicarbonate, HCO3 1-. Bicarbonate has the ability to donate an H to our water and turn into the water into hydronium ions, and this would cause the hydronium concentration to go up and the solution become acidic. Or bicarbonate can function as a base, where if we look at this, the water loses a hydrogen, the bicarbonate gains a hydrogen and turns into H2CO3. This increases the amount of hydroxide in solution, which would make the solution become basic. This would be something where, because this can behave either as an acid or a base, the bicarbonate is something that would be known as a species that is amphiprotic. Another example of something that's amphiprotic is water, H2O. Looking at an example of this water with hydrofluoric acid, the HF loses or donates an H plus to the water molecule. The water molecule gains an H plus ion, turning into hydronium. In this case, the water molecule is behaving as a base by accepting a proton. Or water can function as a base. In this case, we can see the water starts out as H2O. Meant to say where water performs as an acid. It starts out as H2O, and the water donates an H plus. The water turns into OH minus. The ammonia gains the H plus and turns it NH4 positive. In this case, our water molecule is functioning as an acid. Let's take a look at if something's amphiprotic, what does it do if we find that amphiprotic ion present in a salt? For example, sodium bicarbonate. When sodium bicarbonate goes into solution, it splits into separate sodium ions and bicarbonate ions. The sodium ion, because it's the conjugate acid of the strong base sodium hydroxide, the sodium ion is a spectator ion and will do absolutely nothing. Now, will the bicarbonate behave as an acid or a base in solution and make the resulting salt solution acidic or basic? To answer our question, will bicarbonate, when in solution, make an acidic or basic solution? It depends on the Ka value for the acidic behavior of bicarbonate or the Kb value for the basic behavior of bicarbonate. Now here again we see the reactions for bicarbonate behaving as an acid and also as a base. For its acidic behavior, bicarbonate has a Ka value. For its basic behavior, it has a Kb value. Looking at bicarbonate's Ka value, we see that it's 4.7 times 10 to the negative 11. For its basic behavior, bicarbonate has a Kb value of 2.3 times 10 to the negative 8. What we can see here is that the Kb value for bicarbonate's basic behavior is larger than the Ka value for bicarbonate's acidic behavior. Consequently, if put into solution, it's going to behave more as a base than as an acid, and the resulting solution of a salt that has bicarbonate would be a solution that is basic. We have now one last thing to cover on salts and aqueous solutions created from salts dissolving. Let's start out with an example we're familiar with, something such as table salt, sodium chloride. Now, when an acid and a base react, they're always going to form a salt and some water. This is an example of a double replacement reaction. In this case, the HCl and NaOH react we create our salt, sodium chloride. Now in salts, the positive ion is typically the conjugate acid of a base. In this case, our base would be sodium hydroxide, the strong base. And then likewise, the negative ion in a salt is typically the conjugate base of an acid. In this case, our acid is HCl, the strong acid. Both of these ions, the sodium and the chloride ion, when in a salt, are going to be spectator ions, doing absolutely nothing to alter the pH of a solution. Now, each of these ions, the sodium and the chloride, again, the sodium is the conjugate acid of sodium hydroxide, the strong base. Consequently, it has no strength as an acid. It has a Ka value equal to 0. Also, the chloride ion is the conjugate base of hydrochloric acid, the strong acid. Because it's the conjugate base of a strong acid, the chloride ion has a Kb value also of 0. It cannot function as a base. That's why the chloride ion is a spectator, and also why the sodium ion is a spectator when they're ions that are in salts. Now, another way to look at this is if we look at the self-ionization of water, where a small fraction splits into H plus and OH minus. If some chloride ions come along into the beaker, and the chloride and H plus ions go bump in the beaker, these two ions are going to remain separate. Consequently, the H plus ion concentration is not altered, and there's no change to the solution pH. Now, because both ions in this salt are spectator ions, we would say this salt is going to make a solution that is neutral. There's another reason why it's making a neutral salt. The Ka value for sodium Na plus functioning as the conjugate acid of sodium hydroxide is 0. The Kb value for chloride ion is also 0. In any salt, if we compare the Ka of the positive ion to the Kb of the negative ion, and they come out to be equal, that's always going to make a salt that is neutral. Take a peek at another salt, sodium fluoride. The sodium ions are going to be a spectator again because they're the conjugate acid of sodium hydroxide, the strong base. It has a Ka value equal to 0, meaning it indicates it cannot function as an acid. The F minus ions, on the other hand, are the conjugate base of the weak acid HF. It has a Kb value greater than 0, indicating the F minus ion can function as a base in solution. F minus ions in water, if they go bump in the beaker with H plus ions, are going to make the weak acid molecule HF. By forming weak acid molecules of HF, the H plus concentration in the water is going to drop, and the solution would become basic. So the salt, sodium fluoride, is a salt that would end up creating a solution that is basic. Now, another reason for this, if we compare the Kb and Ka values of the ions in the salt, the Kb of the F minus is greater than the Ka for the Na plus, and because the Kb value for the F minus is greater than the Ka value of the Na plus, this would make a solution that's going to be basic. You need to make a correction back here. This F minus ion up here was meant to be OH minus from the self-ionization of water. What happens is when the HF go bump, we make HF, H plus goes down, so there's now more HOH ions than there are H plus, and the solution would be a solution that is basic from sodium fluoride being dissolved in water. The strategy of comparing Ka to Kb values in salts is mainly useful for if we have a salt that's made where we have two non-spectator ions. An example would be ammonium cyanide. The ammonium ion is the conjugate acid of ammonia, which is a weak base. Therefore, ammonium has a Ka value that's greater than 0. This would be a non-spectator ion. The cyanide ion is the conjugate base of the weak acid HCN. Therefore, since it's the conjugate base of a weak acid, cyanide would be a non-spectator ion. It has a Kb value also greater than 0. Comparing the non-zero Ka and Kb values of the ammonium ion and cyanide ion, we can see that the Kb value of the cyanide ion is greater than the Ka value of the ammonium ion. Consequently, this salt, ammonium cyanide, would create a solution that's going to be basic. The remainder of this video is now going to focus on doing pre-lab calculation number 5, which is how to figure the pH of a solution made by a metal ion that causes a solution to become acidic. For this problem, we'll use the Rice strategy. To write the equation, we have our MnH2O6 2+, the manganese ion surrounded by a sphere of hydration. They're going to give up a hydrogen. So on the product side, what happens is the number of waters goes down by 1, becomes H2O5, and we now have an OH added on here as part of the overall structure, which would represent the one water molecule that's lost in H+. The charge has changed from +2 to +1 because by giving up an H+ ion, the charge is going to go down by 1+, because that 1+ is now over here on the water where it formed a hydronium ion. We're given in the problem that the initial concentration of the Mn ion is 1.0 molar. When we reach equilibrium, we're going to go up by X of our hydronium, and this is going to go down by X. We can see that the Ka value for this is a very small number. Consequently, the size of our X is going to be extremely tiny. We can then remove the X from our 1 minus X expression to make our math a little simpler. We set up our Ka expression, and all we have to do is solve for X, and X will give us our hydronium ion concentration. Solving for X, we find our X is our hydronium concentration. We get 1.92 times 10 to the negative 6 molar. Our pH is the negative log of the hydronium ion concentration, so we can put our hydronium ion concentration into the expression and solve for our pH. Solving for our pH, we get a pH of 5.72, indicating that our solution from this particular material is acidic.